We have a lot more to show you. Well, again, good morning, everybody. I'm delighted to have had this opportunity to show you one aspect of my research, which has dominated my life for quite a long time, actually. And I want to review what we know now about the lower all red sandstone, and also to show that there are still enigmas present in these sequences, and that there are also some exciting new avenues of work that are recently published or are currently in being tested. We start, just generally speaking, with the mid-Silurian to early Devonian. We're looking at mid-Silurian. This is a BGS slide, and the dates are slightly wrong at the top there. But if we're looking at the Ludlovian through to the the first stage of the Lower Devonian, the Lochovian, then we're looking at between about 425 to about 410 million years ago. The amalgamation of Laurentia and Baltica in the mid-Silurian gave rise to a major northern continental area called Laurussia. And in the south, we had the amalgamation of Cornubia and Avalonia. And you can see on the right-hand diagram the convergence of the embryonic Gondwana with Laurussia at that time. And of course, the one thing I think has been rather neglected in Welsh geology is the impact of the Arcadian deformation event, that is between the Caledonian and the Bruscan, which happened in latest Lower Devonian time, the Arcadian deformation, because it gives rise to quite a variation actually within the old red sandstone sequences in South Wales. So that's the general setting then of where we are. I mean, we have the development of external basins like we see in the Anglo-Welsh Basin, and of course we have development in the north of these intermontane basins in Scotland and in Ireland. So when we look at the distribution of the old red, there's a diagram you all know in the Anglo-Welsh Basin. We're looking at an area of outcrop of something of the order of 20,000 square kilometers. We're blessed with such great outcrop of these lower all red sandstone rocks. And additionally, of course, we have a big thickness variation between 2.8 kilometers and 4.5 kilometers in total thickness of the lower all red. And that's what I'm concentrating on today. I'm not going to talk at all about the upper all red, just the lower all red, which is, of course, of Silurian and Lower Devonian age. The outcrop is affected by, was later affected by Veruscan tectonics. And so as we move from east to west across the belt, we actually get more and more involved in the Veruscan, that is the Permian deformation. And that's why the rocks in Pembrokeshire are so well repeated by Veruscan folding and faulting, and where we have, in fact, the beautiful coastal outcrops. Just here to remind you that the nomenclature of the old red sandstone across the whole Anglo-Welsh Basin has been recently revised by BGS to get rid of all the old stratigraphic terminology, because it was a real case of stratigraphic diarrhea when you looked at all the local names given from the borderland right across to Milford Haven in the west. So the lower all red now is essentially called the Diglathii group, and that is divisible into two subgroups, the Milford Haven subgroup and the Cochison subgroup. And the Milford Haven subgroup is Silurian in age up to the late Lochovian at 410, as you can see on the right-hand side. And then the Cocheston subgroup is latest Lochovian and Pragian and into the lower Emsian. And then in the middle to late Emsian, we had this major and a very important Arcadian deformation phase about 395 million years ago. So they've tried to standardize the nomenclature across the whole basin now, over the whole 20,000 square kilometers, which I think is a good thing, and even better from the point of view of the work we did in Pembrokeshire over all those years. They've used mainly the Pembrokeshire nomenclature right across now to the Welsh borderland. So the paleo drainage patterns for the lower All Red, as you can see, mid-Pridley. Pridley is the highest stage of the Silurian. From mid-Pridley into the mid-late Lochovian, that's the first stage of the Lower Devonian, hasn't been really looked at in detail for a long time. This is diagrams from paper by John Allen and Steve Crowley from 1983. So this is of some antiquity now, and both these diagrams are wrong. They were reproduced in a recent PGA paper, but there's a lot of anomalies in this configuration of drainage, particularly in the Anglo-Welsh Basin, and its connection across to the Dingle-Shannon Basin in Ireland. And as many of you know, I've also had a great amount of interest in the lower All Red of the Dingle area and produced a book on it in 2018. And also that was my assistants there were PhD students in Bristol and Aberdeen that worked with me in Dingle. So there's a connection between the two, and this is one of the new perspectives I'll mention a bit later on. So that then gives you an idea of the spatial area of lower All Red rocks I'm going to be looking at this morning, and also some of the time phenomena that we're dealing with. Basically from early Ludlow, which is about 425 million years ago, up to the Lochovian, which is 410, and then a little bit into the Pragian of the Cocheston group at the end. So let's turn our attention then to the lower All Red of Pembrokeshire. And and this is a map that you're all acquainted with. This is from Gareth George's field guide. And Gareth and I are we're a bit late actually in getting this thing finished, but hopefully by the end of this year, we'll have the new book out on the red rocks of Pembrokeshire. And this is one of the figures that we'll be using, showing the effect of Veruscan deformation on the mid-Paleozoic rocks of South Pembrokeshire. And by virtue of these major structures, particularly the faults, the 5 big faults, which are important in shaping the architecture of the lower All Red of Pembrokeshire, are the Benton Fault in the north, the Musselwick Fault over near Marloes, the Wennell Fault, which is also in the Marloes Sandy Haven area, and then the big one, of course, is the Rittick Fault, which shapes Milford Haven. And in addition to that, of course, there are the big folds, the Winslow Burton anticline, which contains the Cocheston group, or Cocheston subgroup, I should say. And then to the south of the Rittick Fault, we've got the Pembroke syncline, and we've got the Castle Martin course compound anticline. So by virtue of this deformation, both fault-in and fold-in, we have these marvelous repetition of outcrops that many of you've seen in the past in these coastal sections of Pembrokeshire. This is a historical picture. This was the year really it all kicked off. There's John Allen on the right and me on the left, a lot younger than we are now. Poor John, of course, passed away a year ago, so I lost a really great friend and colleague then, and this is the first time we got together really in 1973, and you can see that's Freshwater West, and it was from this field meeting that the whole research effort was initiated. That took us 8 years to remap the Old Red, the lower Old Red of Pembrokeshire, and it kicked off on this particular field trip down in Pems. The folding in South Pembrokeshire is made up, and I mentioned the big macrofolds, and the macrofolds like the Pembroke syncline and the Castle Martin course anticline, and also to the north of the Ritic Fault where it's even more intense. The macrofolds often have mesofolds on their limbs, and this is a beautiful pair of parasitic mesofolds on the southern limb of the Pembroke syncline on the on St. Anne's Head, Cobbler's Hole, where yesterday they recorded winds of 92 miles an hour. But this area was fortuitous in Bristol to have people working with me on this Vryscan geology, and particularly Dr. Paul Hancock and his PhD student Bill Dunn. And Bill Dunn did a remarkable piece of work on the structure of the lower Old Red north of the Ritic Fault, and it was the integrated nature of the work, the amount of structure we learnt from the structural geologists, and the amount of sedimentology the structural geologists learned from us was quite remarkable. And the two integrated to actually help to understand a lot of the disposition of these this Old Red architecture, both sedimentologically and structurally, on the South Pembrokeshire Peninsula. The sequence, as always, has been subdivided. This again from the new BGS publication, shows the Milford Haven subgroup on the left, up to and including the lower Old Red that we see beautifully both north and south of the Ritic Fault, and also north of the fault, of course, we get the Cocheston subgroup as well, which one of my first PhD students, Richard Thomas, worked on in detail from the point of view of the sedimentology, structure, and palynology of those rocks back in the late 70s in Bristol University. And then there's correlative sections you can see from the beacons and the Kennan Valley and the West Borderland, and the nomenclature now is taken across. You can see the old nomenclature is there on this diagram as well, but things like the Freshwater West formation now are taken right across the whole outcrop area to the borders, as are the Moor Cliffs formation. I'll point out here also, of course, that one of the big discoveries that we made in the late 70s was the presence of these remarkable airfall tuffs, which is called TT, the Townsend Tuff, and that you can see is a marker bed going across the whole 20,000 square kilometers of outcrop from Skocombe Island, offshore Western Pembrokeshire, right over to Ludlow, where we actually drilled it, cored it at depth. And in addition to that, about 90 meters above, right on the Siluro-Devonian boundary, that is the Predilly-Lochovian contact or boundary, there is the CPL, which is now called the Chapel Point Limestone Member by the BGS as a regional marker. And that is something, again, I'm going to come back to in a little while as a very important indicator of basin evolution in the lower Old Red sandstone of South Wales. First of all, a quick look at, I think, a remarkable piece of work that has recently been completed just pre-COVID by one of my students who was an incredible geologist, Rob Hillier, who lives in Pembrokeshire, and Sue Marriott, of course, who's now in Cardiff. And this was published in 2019. And Rob had worked with some of the BGS guys in the central South Wales Pontyclechau area, and of course he'd worked with me a lot in Pembrokeshire. And his vision was remarkable in looking at the evolution of some of the very earliest, that this is mid-Silurian Old Red of central South Wales and Pembrokeshire. These are from the paper that, if you haven't seen it, it's very well worth reading, by Hillier Marriott et al. And you'll notice here that we've got two sketches from early Ludlow, that's about 425 million years ago, to late Ludlow, which is about 423, 422 million years ago, where we had inversion of the Welsh Basin. In the upper diagram, you'll notice that the Welsh Basin to the north of where Pembrokeshire is today was really a shallow shelfal sea. And then to the south, the brown area was an area of landmass called Britannia, which was its position was governed by the Bristol Channel fault zone as we know it today, but that was supplying sediment to the north into the shallow marine waters of the early Ludlow. So the oldest unit in Pembrokeshire of red beds, of fluvial continental red beds, is the Red Cliff Formation, and they are southerly derived, and they came from Britannia to the south. Now, what's not shown on here, and not on the later diagram, is that the overlying Albion Sands Formation is an axial system that was derived from the west, from a source area that we don't see today and don't really know where it was. But what we do know, it was very rich in volcanics. I'll come back to that afterwards. And then in mid-Ludlow times, there was basin inversion, which meant that the landmass was now to the north, this Piedmont area to the north, and then it gave rise to a pediment plain or an alluvial plain. And of course, the sea level varied a great deal, in addition to the tectonic drive. So because of that, what Rob Hillier and Sue Marriott evaluated was that there was incision. There was incision that took place in three main areas, as you can see in this diagram, in mid-Pridley time. This is about 422 million years ago. In Freshwater West area, in Pembrokeshire and the Souther in central South Wales, and the Russell Valley system over to the east. And these are incision surfaces. Rob managed to map, and it's particularly difficult inland in the Pembrokeshire area because of relatively poor outcrop compared to Pembrokeshire, to see the size of these incised valley fills. And it actually brought home to myself in particular some of the anomalies that John and Alan and I couldn't quite understand when we did the original mapping down in Pembrokeshire, particularly with the Freshwater East Formation, the basal formation in the Pembroke Peninsula. This is the Freshwater East Formation at Freshwater East itself. On the left, there's a very simple little log, and that shows where some of these, there's a basal conglomerate, which is unconformable on the underlying Wenlock in Freshwater East and in Freshwater West. And then amongst the mud-rich red beds, which you can see on the main photograph, there are some heterolithic gray units, green-gray units, which when John and I mapped this way back in the late 70s, we found quite a lot of fossiliferous material, particularly plant remains, which we gave, of course, to Diane Edwards, the doyen of Old Red Sandstone paleobotany. And Diane even refers to our bed numbers for her identification, not the identification, but the positioning of where her samples came from. So this is some of Diane's work from an outstanding paper in 1979, showing mainly Cooksonia, these tiny little primitive first vascular plants that were identified from that area. Now, these were really quite small plants. The maximum height they grew to was about 2 centimeters. There's a number of different genera in here. There's Salophylites and there's Hostinella as well. But Cooksonia dominates this slide. and that they're the ones that Diane concentrated on. But they were small. They started to become prolific in these late Silurian rocks, and they started to actually bind the sediment, but they didn't have very big root structures. Now, recently, in this 2019 paper, in addition to the plant material from those gray heterolithic units, there was also a very, very good assemblage of paleomorphs. So the spores you see here, Chelinospora, have been correlated with the spore zonation of late Silurian rocks in the Cantabrian Mountains. And they've pinpointed the fact that the freshwater east formation is based on these spores is of mid-Pridley age. So they're about 421, 422 million years old. And they're very accurately dated now because of not only the plants, but also, and more specifically, from the spore assemblages. And that was done by Ken Higgs of University College Cork. So magnificent preservation of these. So if you look at a panorama at Marloes through the section, one of the things that we found a puzzle when we first mapped this area was going from right to left. You can see in the corner over on the right-hand side, the Red Cliff Formation, the earliest red bed sequence, overlain by the Albion Sands Formation, which was derived from the west and full of volcanic detritus. They really are volcanic arenites, and that's about 85 meters thick. And then we get on to Gatesholm Island. And in Gatesholm Island, we go straight into the Moor Cliffs mud rock sequence, where it's just muds and calcaretes. That's all you see until you get to a unit which actually puzzled John and myself because it was conglomeratic. The conglomerates were extraformational. They were petromic conglomerates, and they also contained gray-green beds with Pachytheca, Lingula, Oncus, and plant material and fish fragments. And then we went back into the mud rocks, and we were always concerned what that was. We thought, how did it fit into the mud belt, which is the Moor Cliffs Formation? Well, it transpires, of course, now that Hilly has mapped it in as a part of an incised valley fill. So if you look at this great diagram, it's a cartoon. You can see Gatesholm on the left-hand side, and Gatesholm has, in the middle of the island, splitting up the Moor Cliffs Formation, has the incision surface. So there's a sequence boundary going through the middle of Gatesholm Island, which you can track then through Freshwater West, which you can see on the left-hand side, and over to Freshwater East, which you can see on the right-hand side. So, as it says in the notes on the right, the lateral extent of the IVF, that's the incised valley fill, is uncertain. The incised valley fill location in the northwest seems to be tectonically controlled, which I totally agree with. And then the thickest deposits of the Freshwater East Formation, which is part of the incised valley fill, are south of the Rhytic Fault. And the orientation of sediment coming into that incised valley fill, which had a relief of about 60 meters on it, indicates sediment transport from the northwest, mainly on cross-bedding, but also, I think more specifically, on imbrication of clasts. Because if you have fluvial clasts, the AB plane of the clasts tend to dip upstream, so you can use imbricate clasts to actually work out the paleoflow direction. I think that's a wonderful example of very detailed work, and this is in an area where it was very good outcrop. Over further to the east, of course, you then go to the Pontychlechau area, which is shown on the right-hand side of this terrific diagram. Again, a cartoon, and you can see FWE is the Freshwater East Formation. So if we start at 1, this is the basal old red sandstone unit, the Red Cliff Formation, which you see, of course, in South Pembrokeshire, in Marloes area in particular, and it does have a slightly diaphanous but conformable contact with the underlying marine Silurian rocks of the coralliferous and grey sandstone group north of the Rhytic Fault. So the first line, you can see the Rhytic Fault, then you see the Musselwick Fault. So we go between the two, we go from the Red Cliff Formation then with a slight hiatus into the Albion Sands, which is then interfingered with the Lindsway Bay conglomerate, which is an alluvial fan coming in as a lateral infill, which is the same age as the Trig beds at Pontarlechai. And then you have into the mud belt of the Moor Cliffs, and then the incisions. So the incised valleys are shown in this cartoon. So you can see where 3 is where the main inversion of the Welsh Basin took place. So I think this is a remarkable piece of detailed work that's just been published and which built upon and improved very much the framework that we'd set down for the very basal red. Look at the divisions here. We're looking at all Silurian divisions. The Ludlovian is split into the Gostian and the Ludfordian, and we got no real dates at the bottom here, but it could well be that the base of the Red Cliff Formation is even Wenlock in age. So we have this system right up to the top of the Pridley, and if you take the top line of the diagram, that is basically the line of the Chapel Point calcrete limestone member. So I do recommend that you look at this, and maybe next year, later this year or next year, when the book appears, we'll go down here and go through this with the South Wales GA. I'd love to show you this new interpretation of the very oldest old red in Wales. Okay, let's now turn our attention to the main basin fill, and we'll go now. You can see here the stratigraphy is shown on this diagram, both north and south of the Rhytic Fault. The Arcadian unconformity is indicated in the key on the bottom left of the diagram. The Arcadian unconformity, of course, separates the lower Old Red from the upper Old Red sandstone, Sprinkle Sandstone subgroup. And so there's no Middle Devonian at all in the Welsh Basin. And then north of the Rhytic Fault, of course, we have the preservation of the Pragian unit called the Cosheston subgroup, which then again, that is topped by the Arcadian unconformity in that area between the Rhytic and the Benton faults. So, okay, we come on to some enigmas now, which have been hanging around for years. There are 5 of them. There's the mud rocks, which is a dilemma which I think we're quietly sorting out, particularly with the help of Paul Wright and Sue Marriott of Cardiff. There's the tuffs, which we still regard as a very key unit over the whole of the Welsh Basin. There are the calcretes, which indicate the basin shutdown. Then there's the evolution of the sand bodies particularly in the Freshwater West Formation. And then finally, of course, as a result of the influence of the precursor of the Arcadian deformation, we have alluvial fans and the big rivers coming in at the top of the lower Old Red in both south of the Rhytic Fault and north of the Rhytic Fault. So we look at these in turn. The Moor Cliffs, okay, the Moor Cliffs Formation is a formation up to about 1 kilometer thick. It is over 70% mud rocks. In other words, both claystones and siltstones make up, and this is one of the, where did all this mud come from? It also contains minor sand bodies. It says fine grained, but that really is not right. It's coarse to fine grained. High width to depth ratio abruptly interfaced with the mud rocks, which I'll come back to in a second. There's no classic upward finding sequences of alluviation in the Moor Cliffs Formation, and then we have all these different mudstone fascies. And we'll look at these in turn. So first of all, just a lovely view looking from the west side of, the east side of Manorbier along the coastline towards Barafundle in the far distance. The rocks are vertical. They're younging from left to right. In the Moorcliff headland, you can see in the middle distance there, where some of the big slots are cut out by sea erosion, are where some of the major tuff horizons are, the airfall tuffs in the Moor Cliffs. And then in the foreground, we've got some of the Freshwater West. So it's younging from left to right, and of course there's offsets because of dextral wrench faulting all along this coastline. Okay, the mud rocks. First of all, we have mud rocks which appear massive, and it's, as it says there, with or without scattered clasts or lenses. And then the one on the right shows ones with the tiny little calcrete particles, sort of small gravel-sized particles, and also some sand-sized particles. Now, one of the things that's been discovered very recently in the North Sea, in younger rocks in the Triassic, is a new rock type of mud rock called leucite. And this is lithified loess, i.e. windblown dust, aerosol dust. And they've now been well documented in the Triassic red beds of some of the subsurface North Sea reservoirs. Beautifully seen, and you can see them in thin section, and you can see that under high magnification. Now, leucite has some very unusual clay minerals, particularly a clay mineral called torsudite, T-O-S-U-D-I-T-E. And one of my friends in Aberdeen, who's another ex-Swansea PhD, probably one of the world's most eminent clay mineralogists, called Jeff Wilson, he is now working on this, and we've been collecting recently from Llanstefan to see if we can identify leucite in the mud rocks. If we can identify mud rocks with loess deposits. Now, these tiny clay particles of todosite have a random grain fabric. So this is work in currently ongoing, and I'll keep you posted on how we get on. The problem with pellets is that they are very difficult to see, and they tend to get compacted with very shallow burial. So in rocks as old as the old red sandstone, unlike the Permian or the North Sea, the burial depth is such that the pellets may become amorphous. Then the second type of mud rock, of course, are ones that are exclusively and massively bioturbated. So you get bioturbated mud rocks as well. Many of these are subaqueous mud rocks. They weren't subaerial. Then we have roots. Now, when we showed Diane these initially, she didn't believe it because Cooksonia is only 2 centimeters high. And look at the size of some of these roots. And it transpired that when you look at them in detail, these aren't roots of plants. They are anchor holdfasts for giant fungi. And the giant fungi is called Prototaxitis. And it seems that the landscape on this Piedmont area, this coastal plain of alluviation and cliffs, had lots of Cooksonia, but also these giant fungi present as well, giving rise to these large root-like structures in some of the Moor Cliffs mud rocks. Of course, one thing that is ubiquitous in the Welsh Old Red are calcite-rich or calcic vertisols. Paul Wright from Cardiff has done a huge amount of work on these, and you have these wonderful arcuate features called pseudoanticlines, where the calcrete rods are orthogonal to the surface of the they should be called pseudosynclines, really, of the bowl-shaped depressions, which are caused by seasonal wetting and drying of the clay minerals. And when you see them today, they're called gilgai structures. When you see them in modern settings, like in India, in Botswana, and in Texas High Plains, you can see these things evolving today. And these, of course, are very important marker beds. They're indicators of climatic control, and they can be extremely useful basin-wide. And then the other mud rocks, the last one, are mud rocks that were actually deposited in lakes as very, very subtle, very fine, wave reworked laminites. The top right there, you can see how subtle. If it wasn't for these wave polished surfaces, you wouldn't see these. And we're dealing with coarse to fine silt and claystone, which is laminated, undulating, locally rippled, and these are all subaqueous mud rocks. And there's a lot of this also in the Moor Cliffs. So Sue Marriott and Rob Hillier came up with this cartoon. They really like the idea of a lot of the mud being pellet aggregates. Although, as I say, it's difficult to prove because they are diagenetically altered in rocks of this age. But they envisage the Moor Cliffs as being a series of sinuous, low to high sinuosity, sluggish stream systems with ephemeral lakes and ponds. You can see the Gilgai structure, the circle shown on the right and the left, and the calcic vertisols, which are due to that seasonal drying and wetting the clay minerals, while the soil profile is horizonating. So this is a little model. It could be refined, but it's a little model that they go along with. And they don't include in here any Aeolian imprint, which is, as I say, Leucite. And they've actually cut back upon the amount of subaqueous lacustrine type mud rocks that are present in the Moor Cliffs as well. Now, in addition to this overwhelming mud rock, 70% of the Moor Cliffs being mud rock, there are sandstones and there are conglomeratic sandstones as well. And these are the product of what are called superfloods. These are sheets. They may be individual sheets or they may be single sheets. This is a profile by Sue Love, one of my Aberdeen PhD students who worked on the Manorbier, Principe, Conager Pit sections in South Pembrokeshire. In purple is the Rook's Cave Tuff, which is about 40 meters or so below the Townsend Tuff. And then in yellow are some of the sheet sandstone bodies. You can map them in these wonderful strike sections between Freshwater East and Oldcastle Head for many kilometers. And you can see the erosive nature of the underlying surface. Not a great deal of relief on them, but they are erosive. And they are epitomized by, this is St. Bride's Haven. You can see the mud rocks. You can see the embryonic immature calcaretes forming in the mud rocks. And then you see that sharp-based, slightly erosive, sharp-topped sheet flood event. These are allochthonous. These came in as a super flood from the Piedmont across the alluvial plain of the muddy Moor Cliffs Formation. They reworked and they stripped off the top profile of many of the soils, and they can carry quite a lot of quite small pebbles and granules of exotic material across a large area. Now, they're either individual sheets or, like this one at Mill Bay, north of the Haven, they can be multi-story stack sheets. There's John Allen for scale there. And this one we mapped over 10 kilometers north of Milford Haven. And every time we mapped it, it was about 8 meters thick. And it was 3 big sheets, one on top of the other. The middle one was always soft sediment deformed. In other words, there was so much sediment, so fast deposition, so much poor water that the poor water escaped upon deposition and formed deformation structures. So this is a very good example of a multi-story sheet system in the Moor Cliffs. Okay, so what I've looked at then in the Moor Cliffs, I've looked at another cartoon that Rob and I did for the architecture of these sand bodies. We've been looking at the Moor Cliffs, and I've shown you the multi-story sheets, and I've shown you some of the individual single sheet units in this dominantly mud rock succession. But then, of course, we come in the middle part of the Moor Cliffs Formation into this zone where there are 29 airfall tuffs. In other words, 29 volcanic events, but there are 3 big ones. And on here, we've got the Townsend Tuff, which is basin-wide, and the Pickard Bay Tuff, which is basin-wide, and then the Rook's Cave Tuff, which is below the Townsend Tuff, which actually is fairly local to Pembrokeshire. This is what it looks like, a magnificent exposure of it on Oldcastle Head. You know, you need permission from the School of Artillery to go and see this one, but it's a great example. It's normally between 2 and 4 meters in thickness. It comprises 3 superimposed airfalls. This is the discovery locality that John and I made. He's got his left boot on the top of Fall A, which is a small fall, and which in fact is everywhere, even in the cores from Ludlow, everywhere covered in trace fossils and fecal debris. And then Fall B is a thicker one, which extends up to the top of the silicified dust tuff, and everywhere, again, even in cored sections, you see the scoured surface at the top of Fall B, and that obviously was a major event over the whole basin. It's probably a tsunami horizon, which formed the scouring over that whole distance. And then from there to the top, we've got Fall C, where the top of which is not silicified. So the weathering profile and the grain size profile are like inverse. So you're from the Fall A, the crystal tuff with the burrows and the fecal debris, through the crystal tuff with wavy bed forms. These tuffs were deposited subaqueously. Then the big erosion surface, which is probably related to some major geological event like a tsunami, and then into the Fall C, which goes again from the erosion surface up through a crystal tuff into a dust tuff to the top. So there's typically one. It should be typically 2 to 4 meters thick, and of course, beautifully seen in everywhere across Wales, where even the new road cut at Red Roses goes right through a magnificent section of the Townsend tuff bed in the new cut in there. So lots of phenomena. Lance Morrissey, another one of my PhD students in Bristol, did all the trace fossil work on these tuffs, and also on the mud rocks and sandstones in Pembrokeshire in the Lower Red. And he's got all sorts of dwelling burrows, escape burrows, fecal debris, and in addition to a variety of walk-in traces. And in them, the bed forms preserved in the tuffs show that they were deposited subaqueously, that they were probably deposited in shallow ponds or lakes, which were ephemeral, locally at least, although it was deposited over the whole 20,000 square kilometers. I mean, looking at a massive amount of ashfall for these tuffs, probably derived from about 500 to 800 kilometers away, probably the other side of the Iapetan suture, somewhere in Russia, where the volcanic center was, that spread these amazing plumes over Pembrokeshire. One thing I should have mentioned, that Fall A, the one that John had his left boot on, has been now very thoroughly radioactively dated using zircons, and it's dated as 420.03 million years, plus or minus 0.6, so plus or minus 600,000 years. So it's an incredibly accurate date, and it's very, very close to the Silurian-Devonian boundary. So there's the Rooks Cave tuff. It's the last one to show you. The rocks are young in from right to left. There's John, and here you stand in one of these ponded tuffs. This one is a double airfall. This is on Priest Nose, just on the east side of Manabia Bay, and you can see the tuffaceous deposit there. You see it thinning towards the east there, and these are ponded units. And on the lower surface, there were some absolutely remarkable trace fossils preserved beneath this fine ash. Okay, coming to the top of the Moor Cliffs, we come now to what the survey renamed formally as the Chapel Point limestone member. Again, over in East Wales, it was called the Bishop Froome limestone, but it's now got the same name right across the whole outcrop area. This is again a sketch courtesy of Paul Wright, showing the profile of a typical calcic vertisol, where you have mud-cracked zone A, and then zone B, where you get these pseudo-anticlinal, these seasonal wetting and drying of clay minerals, giving rise to these slicken-sided slip plains, and then the calcrete nodules and rods that are often arranged orthogonal to those glide planes while the soil is growing, i.e. horizonating. So you go from immature to super mature. So that's the process. And then this is what I'm talking about. You can see these pseudo-anticlinal or pseudo-synclinal phenomena. You can see the orthogonal nature of the rods of the calcrete in the profile B and C here. This is a sort of relatively immature calcrete. And then you get ones like Llanstefan, where there are about 6 of them, and they are massive. These are super mature calcretes. This, don't forget, is a marker horizon. This is the Chapel Point, excuse me, limestone member, and it can be, as I say, mapped over the whole basin, and it's right on the Siluro-Devonian boundary. It's about 419.3 million years is the boundary, and this is slap on it. And what it shows, when you think of a super mature calcrete may take 100,000 years to actually form, and if you got them superimposed one on top of the other, this is Chapel Point itself actually on quality, and here we got 6 of them stacked up. So over 30 meters of mud rock, we have 6 big calcrete horizons giving rise to this limestone, this Chapel Point limestone member. And so we're looking at a great deal of time where these soils were allowed to horizonate one on top of the other, where the host was mud rock only. So there was nothing else coming into the basin. So basically the basin shut down, and everything changes in the lower Old Red above that contact. The provenance changes, the detritus changes, the whole system of architecture of the sedimentary units, the sandstones change, the fossil fish start coming in. Everything happens above the Chapel Point limestone member. So that is the type locality on the south side of Caldy Island. So come now to the Freshwater West Formation. So I've shown you the TT, which is the Townsend Tuff Horizon, how important that is at 420.03 is a marker bed over the whole basin. The CPL, or the Chapel Point Limestone Member, as it's now officially called, is the basin shutdown horizon. And then it must have been, this is work that we're currently trying to piece together and write up as to why the basin shut down at that time, right on the Pridilian-Lochhovian boundary. That is the Silurian-Devonian boundary. It just shut off, and it must be a tectonic drive that did it. And sediment was starved, and that Chapel Point system of calcretes, superimposed calcretes, was allowed to horizonate over many hundreds of thousands of years before the next supply of sediment came into the basin. Again, probably in response to a very early pulse of Arcadian deformation. So we're moving up now into the Freshwater West Formation. We're moving up the top of this cartoon into the different sorts of sand bodies, which again evolve from quite fine-grained and sinuous alluvial deposits, river deposits, up into some sheet events, and then into large multi-story braided river deposits at the top. So let's look at these now. Of course, best seen in my favorite section in the world, probably the best section of mid-Paleozoic rocks in the whole of the UK is Freshwater West. And I imagine after yesterday's storm, this would be stripped clean now. It would be lovely to go and look at it again. But we've measured all this on a sort of millimeter scale over many years. So you can see that where the TTB is up here. You can see the Chapel Point calcrete member here. Then there's the Freshwater West Formation, and then the Ridgeway conglomerate, and then the yellow is the upper Old Red Sandstone. So the Arcadian conformity is here between the Ridgeway and the overlying Sprinkle Sandstone subgroup. Okay, and this is the Flimston Bay Fault, which you can see is a dextral wrench, which increases in throw as you track it south towards the edge of the Pembroke Peninsula. So the pictures you're about to see are from this wonderful, wonderful locality. You could spend a whole weekend field trip on this one section. It's so good, and it shows so much stuff. Okay, at the base of the Freshwater West Formation, you have inclined heterolithic units, which are quite coarse-grained. This is Manabir. This on the left is the top of the underlying Chapel Pond calcrete member, and then there's some erosion by the sea, as you can see along this contact. There's a conglomeratic base to the Freshwater West Formation here, and these surfaces you see are closing towards the sea. So this is the coarse-grained heterolithics you find at the base of the Freshwater West Formation. Biggest rivers, but relatively fine grain apart from the basal units, and they're inclined. So they are possibly related to large-scale point bars in these rivers. This is Clan Stefan, where again, there's the base is on the right over here, as you can see, and then you can see the inclined heterolithics here coming in, and it's got a very mature calcretized top, then the next surface. So we got an upward fining sequence, fine-grained heterolithics, and this is quite normal in the lower part of the Freshwater West Formation deposited by relatively muddy, sinuous, meandering river systems. And then as you go into through the section, you start then getting the effects of superfloods, and these provide sheets, and the sheets may be flat-bedded, showing high flow regime, or maybe low flow regime with big crossbeds in like this, or even better like this. So there's the underlying calcrete. Rocks are young in left to right, and then you can see there's a interclass conglomerate here at the top of this cycle, and then you go into cross-bedded, and then plain bed, upper flow regime sandstones, and then cross-bedded again. So you get very pulsed flows in these sheet floods, giving rise to these units, which are so beautifully seen in this section in the middle part of the Freshwater West Formation. Then also you get heterolithics in the middle part, and then these monstrous burrows. I mean, these can be up to 1 meter long. They can be a decimeter in diameter, as you can see a conical pit. This is a top surface looking down on these, and these, of course, are called, or were called, and people still call them Beaconites burrows. These are big burrows, and they are burrows that the animals dwelt in for many years. People didn't know what they were, but they now have been identified as Aeoarthroplurids. This is a sketch of them here. Beaconites barrettae. Then there's all sorts of traces associated with these upper parts of these fluvial cycles, including fecal debris, trackways, even fish tail marks called indigna. You see the switching of the fish's tails. But the big things are these Aeoarthroplurids. You see they go down to the water table. So there's even a possibility of mapping, not that we've done this, mapping paleo water tables in the Freshwater West Formation in South Pembrokeshire, because there's such a profusion of these large Aeoarthroplurid burrows. You know, they're like big millipedes that produce these wonderful trace fossils. This is just a section, again, from Gareth's book, showing just 100 meters of the Freshwater West section of the Freshwater West Formation. And I was showing you the lower parts, the heterolithics down here. I showed you some of the sheets here. I showed you the heteroliths with the Beaconites beds there. And we're now up here in the multi-story braided river part with exotic gravel coming in for the first time into the basin, including there's exotic debris like quartz pebbles. There's a lot of lithic debris. There's a lot of calcrete debris and there's fish snouts. You can see there's a snout here of a pteraspid fish, which came along as bedload, and really we didn't find much in the way of preserved whole fish. We found them as disarticulated bedload fragments in these conglomerates. And this is what these multi-story braided fluvial systems look like, with down-climbing dunes, big bar forms, and just absolutely superb from the point of view of working out paleoflow directions. The rocks are here are vertical, of course. They're younging from left to right. And this is another model by Rob and Sue, showing a cartoon of these braid bars, down-climbing dunes, lunate dunes, some splays, and the occasional calcrates, which are reworked during high flow discharge. So that's the model. So finally, we come to the last part, which is now, and again in response to this, it's the whole thing's upward coarsening in response to the oncoming Arcadian deformation event. And so we start then now with the fans coming in, and then the coarse-grained material in the Cosheston. So we've got the Ridgeway up to 387 meters thick, and this is coming from the south, from a resurgent Britannia, if you like. It's coming from the Bristol Channel Fault Zone. The debris is exotic, mainly lithic clasts. There's a volcanic clasts, and there's low-grade metamorphic clasts, which you see in a second. Lots of vein quartz. Rocks are young in left to right, and these are coming in as big conglomerate units from the south. And you can tell that on clast imbrication and crossbeds, that these were coming from a southerly derived land area, which was not very far away near the Bristol Channel Fault Zone. This is just a graphic log showing these conglomerates. Freshwater West has the best preservation of these conglomerates. We're still in the Lochorvian. We're still in the early part of the lower Devonian, and in between the conglomerates, and actually sometimes including the conglomerates themselves, there's a lot of carbonate deposition in the form of calcrates, and in the conglomerates you often get meniscus rims around the clasts of calcite, which are caused by groundwater. So in here you've got groundwater calcrete, and you've got calcic vertisols. And that's very typical of modern alluvial fans. This is near the top, and now you see a lot of green phyllite debris. This is a phylitic conglomerate. These are basement rocks. They would derive from the Briarvarian and that's the late Precambrian and Cambrian of Normandy and Brittany, and that would have made up the landmass to the south of the Bristol Channel Fault Zone, from which these conglomerates were derived, and they drain north. Oops. And this is just to show some of the calcrates within the Ridgeway conglomerate, which are both, as I say, calcic vertisols and groundwater calcrates. Also, you can see some root traces here as well. So this is the model that we came up with recently. This is Rob and myself. And you can see there's the Rhytic Fault to the north and the Benton. This is the hanging wall. There's the Bristol Channel Fault Zone at the bottom. There's the feeder coming in, producing the fan apron. And then you can see the debris flows and these sheet floods with the conglomerates on them coming northwards. Some ephemeral ponded units in the axial system, and some tiny little footwall fans coming off the Rhytic Fault, which was active at that time, as was the Bristol Channel Fault Zone. So we have the footwall and we have the hanging wall. And then we have this southerly derived, beautiful lateral input of the Ridgeway alluvial fan. It's not in its own. This is a sketch from, I think it was Ian Tunbridge originally, showed that here, there's the Ridgeway I've just been showing you, but there's also the Llynarfan conglomerate over here from the Swansea Valley disturbance area. There's the Clinician, which I looked at a long time ago, And recently we've been reworking, and there's a paper in press actually on the Woodhill Bay formation as part of the brownstones. It should come out in 2022 in the GA. So I've been looking at this one again with Paul Wright and with Sue Marriott over in the Portishead area here. So that's another one off these fault zones. So you see a lot going on in this late Lacovian period. So finally, then we now cross the fault to look at the between the Rittick and the Benton, to look at the Winsell inlier or the Winsell anticline extending down towards Pembroke Dock as the Burton anticline. And this is this fantastic bunch of rocks called the Cosherton subgroup, which there's Richard Thomas, one of my early PhDs in Bristol. Looking at the Mill Bay Formation, very sandy. Again, it's upward coarsening, just like the stuff is to the south of the Rittick Fault. This is the Mill Bay again, with a massively deformed unit. This may be actually a mega seismite, because as I said, these faults were active at the time of deposition. So no surprise with fluvial sand, heavy sediment loads, a lot of water, that these would deform. And this is Mill Bay. And we go up then into the Loreni Formation, which now you see a lot of exotic clasts coming in as we upward coursen towards the unconformity at the top. And then finally, this is a log for the new shipping formation in the Cosherton, the top bit. I mean, the Cosherton itself is in excess of 1,500 meters thick. So we have this upward coursening motif to it, and it's capped off at the top, again, by the Arcadian unconformity. And there, believe it or not, is the unconformity. This is a Freshwater West. On the right-hand side, here we've got the lower Old Red Sandstone. This is the top pulse of the ridgeway. I'm bringing my pointer down it. And above, that's upper Old Red Sandstone, would you believe? So that is the line of unconformity where the Middle Devonian is absent. And literally within about 20 centimeters of this contact, you get the first upper Old Red Sandstone fish, Holoptychius, which are found or were found in Freshwater West. So there's the story. We've gone through, or I've tried to show you both the enigmas that still exist, some of the new work. What I should have mentioned with this last few slides is that currently Gareth George and I are working with Andy Morton, who's an expert on heavy minerals, and we've got some preliminary data just before Christmas from Andy, who now lives in St. Ishmael's, on zircon provenance, and we're finding that the zircons are showing phenomenal change in provenance across the top of the Chapel Point limestone member. Again, just backing up the information on this basin shutdown story and this switch of sediment infill in the upper part of the lower Old Red of Wales compared to the Silurian part of the lower Old Red of Wales. And in addition to that, we are tracking all the way backwards from the brownstones of Portishead to the Forest of Dean, to the Senny beds, and to the Cosherton. And even then next year, we're going across to see if we can track across to the Dingle Peninsula in Western Ireland. Big rivers don't disappear. Big rivers of this magnitude, like the Brahmaputra today, go on for a long distance in their flow path. And there's no reason at all why there shouldn't be a link across from the Irish lower Old Red big river systems at the top of the lower Old Red in Ireland to the lower Old Red in Wales. So on that controversial note, I'll end my story and end with the acknowledgements of all the people that have worked with us over the years, both academics and also this great phalanx of PhD students I've been privileged to supervise over the last, God knows, 40 years in both Wales, Ireland, and also the laurel red of eastern Canada. Thank you very much.
Thank you.